Hi everyone, for today's lesson we are going to learn about graphing quadratic functions in vertex form. For today's lesson, to get started, what we are going to do is we're going to learn about the parent function of our quadratic. Our learning objectives for today is for you to be able to say, I can graph a quadratic function in vertex form using the vertex and a table. I can write a quadratic equation in vertex form given a very specific XY table. So this table right here is going to be called a parent function, reflection, stretch shrink, translation table. That is the type of table that we are going to be working with. Before we get started, let's go ahead and talk about our parent function. A parent function is the simplest form of a function. And in this case, for quadratics, the simplest form of a quadratic equation is y equals x squared. And we are going to graph that really quick. So whenever we're creating table of values, I recommend strongly just identifying your values starting from -2 going all the way to +2. So I'm going to substitute -2 into my parent function. So I'm going to write parent function. Is this guy right here. And I'm going to ask myself, what is -2 squared? -2 squared is 4. -1 squared is 1. 0 squared is 0. 1 squared is 1. And 2 squared is 4. One of the cool things about the table is that you will see symmetry around a very specific number or a very specific ordered pair. And that ordered pair is always going to be the vertex. And there will be symmetry, meaning that there will be numbers that are the same, hugging the vertex. Let's go ahead and graph and plot these points. I'm going to plot -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. I'm going to connect these points using a smooth curve. Whatever you do, do not make it like a V shape. These are not absolute value graphs. They are U's, not V's. Please be careful. Now this graph has a vertex, just like absolute value, and it does have symmetry just like absolute value, but it's a different shape. It has a different characteristics to it. It does have a vertex, and that vertex is still at 0, 0, but it has other characteristics as well. Like this shape is called a parabola. And the graph opens up for this parent function, but this is a parabola. This parabola and all parabolas will have an axis of symmetry. Sometimes it is called a line of symmetry. We label that AOS, axis of symmetry. And the axis of symmetry is an invisible, but we will draw it in, an invisible vertical line that cuts a parabola in half. We will draw it. It is located at x equals 0, and I'm going to use a highlighter in order to emphasize that. When you do your homework, I'm going to be looking for you guys to either use a pen or a pencil or whatever, but make sure you draw in your axis of symmetry. This axis of symmetry is always going to be a vertical line. We're going to remind ourselves of that Vux language. Vux meaning that it's a vertical line with undefined slope, and x equals a number. It is also the x part of the vertex. The x coordinate of the vertex. So these two pieces are connected to each other, the x part and our axis of symmetry. Once again, this is the vertical line that is passing through the vertex, and it divides the graph exactly in half. So there's going to be some symmetry on each side, and you'll notice that the points are equidistant away from the axis of symmetry. And it's going to be something that we will use whenever we are graphing. The domain notice we have an arrow pointing to the left and an arrow pointing to the right. So that means that our domain is going to be all real numbers for all quadratics. You can also write it from negative infinity to positive infinity. And our range, well, we have nothing, 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 nothing until we reach what we call a minimum point. It can be minimum or maximum depending on if our parabola is pointing up or down. But in this case, we will have a minimum, and that minimum is located at 0. So it's going to be starting at 0, going all the way to infinity because we have arrows pointing up. Or you can write it simply as y is greater than or equal to 0. And this is a minimum value of 0. So understanding that language of minimum and maximum is going to be something that we will be studying in this section of the unit. Now, please note that there are 3 forms of quadratic functions. The first form that we are going to be studying today is called vertex form. And vertex form has some very familiar characteristics. It is y equals a times x minus h squared plus k. We just talked about a's, h's, and k's, and what's really cool is that a's, h's, and k's, those characteristics of the transformation from the parent function, is constant. All of those rules are still going to be the same with all of the different types of functions. It's just the graphs will be different. This one's going to be a parabola. So that is why we've decided to put vertex form first. The next form that we will discuss is going to be intercept form. And look at that word intercept. That means that we will be able to identify our x-intercepts from it. And it is a times x minus p times x minus q. Where p's and q's are going to be your x-intercepts. And a, that a value is going to remain constant. All of our forms will have the letter A in it. Finally, we have standard form, and that is y equals a x squared plus bx plus c. That will be the last form that we learn about when it comes to graphing. But like I said, today's focus is on vertex form. So today we will learn how to graph quadratic functions in vertex form and the key features of the quadratic function that are easy to identify when it is in vertex form. Well, guess what? Vertex form is super cool because we can identify the vertex very easily, very quickly. So I'm just going to highlight really quick that this is our focus for today. So once again, our vertex form is y equals a times x minus h squared plus k. So let's go ahead and remind ourselves of what a, h, and k mean. Now, there is going to be a reflection in the x-axis if a is negative. Sometimes you will see like a is less than 0 or something to that effect. So that's where the r comes in. A is negative. We will have a reflection in the x-axis. There will be a vertical stretch if the absolute value of a is bigger than 1. If it equals 1, then there is no stretch. It'll have the same exact width as our parent function. But if it's bigger than 1, then we will see that our parabola will be much skinnier. There will be a vertical shrink if the absolute value of a is in between 0 and 1. So we will see that it'll essentially be a fraction smaller than 1. Finally, there is a translation, will be a translation left or right, depending on what h is. And remember that h is, of course, the opposite of what you see inside. And it will move up or down k units. And remember that k units is exactly what you see. On the outside. So h inside is going to be the opposite of what you see. So we'll use like opposite language. Versus on the outside, if you see a plus, you go up. You see a minus, you go down. It's super cool, exactly what you see. The vertex in this form is just like we studied before. It's going to be HK with our axis of symmetry. Remember, your axis of symmetry is based on the X part of our vertex. And if we have ourselves a vertex located at HK, the X part is H. So our axis of symmetry will be X equals H. And we will have a maximum or minimum value. Well, this max or minimum value, I probably should have emphasized that this part comes from the Y part. Y part of the vertex. So in this case, the max or min will be whatever the value of K is. And we'll have a maximum or minimum based on if the graph is opening up or down. So let's go ahead and look at example number 1. So when it says compare, I really want you to know that this space is actually not dedicated for the comparison in words. It's dedicated to a table. And so if you can imagine graphing the parent function of the of our quadratic, that's what our first information is going to be. And what you want to do here is you want to pick ordered pairs from the parent function. So you might want to pick numbers that are like 3, 9, 2, 4, 1, 1, 0, 0, 1, or negative 1, 1, negative 2, 4, and negative 3, 9. All of those would be considered perfectly acceptable. All you need are 3 ordered pairs. 5 ordered pairs are a lot nicer because it gives you that full U shape, but I'm pretty open. So we're going to just keep this simple and choose negative 1, 1, 0, 0, and 1, 1. And the reason why 0, 0 needs to be in there is because it's the vertex, and that is a really important point. Next, we have R. So R represents the word reflection, and in this case, we do have a negative symbol. So that indicates that, yes, we will have a reflection. And how we will address the ordered pairs is we will multiply all Y values by negative 1. So I'm going to take my original ordered pairs in the previous table, and I'm going to multiply all Y values by negative 1 to represent that we have a reflection. So 1 times negative 1 is negative 1. 0 times negative 1 is 0. And then 1 times negative 1 is negative 1. Now, we never work with the X values because X values would indicate a reflection across the Y axes, and that is not what we're doing. When you reflect across the X axes, your positive Y values suddenly become negative because your graph is pointing upside down. So that's the reason why we have Y times negative 1 instead of X. And like I said, we will not be working with X times anything in this class. That's something you explore when you get to the next level. The next column is called S. And S represents stretch or shrink. And in this case, we have an A value that is not 1. So our A value is the number 2. So once again, we call that a vertical shrink or stretch. And because it is a 2, that will be a vertical shrink by a factor of 2. So we're going to use our previous column, and we're going to multiply all Y values by 2, because if you think about it, if it's a vertical stretch, vertical axis is Y, so only the Y is affected. So I'm going to keep all of my X values the same. And my Y values, well, now I'm going to write negative 1 times 2, which is negative 2, 0 times 2, which is 0, and negative 1 times 2, which is negative 2. Finally, we have our translation, and our translation column, that one is dedicated to our H and our K. And now we can talk about X because H affects our X values. So in this problem, we have ourselves our vertex located at the opposite of what we see, which in this case is going to be 1, and exactly what we see, which is 4. So that tells me that my X values will be increased by 1, and my Y values will be increased by 4. So I'm only going to use the previous column, And I'm going to take all of my x values and add 1. So -1 plus 1 is 0. 0 plus 1 is 1. 1 plus 1 is 2. -2 plus 4, that is 2. 0 plus 4 is 4. And -2 plus 4 is 2. These ordered pairs are the only ordered pairs that you are going to be plotting. This already addresses your full transformation. So this is what you plot. So plot these points only. Now, it is possible that you might have learned a different approach for graphing quadratics in a different class. Please know that we will use that approach for the other forms, but for this class, I really want you to become familiar with these tables because we use this table throughout all of semester 1 we use it throughout some of semester 1, but a lot of semester 2. So I really want you to feel comfortable with this idea of using a transformation table. All right, let's go ahead and plot these points. I have 0, 2, 1, 4, and 2, 2. Please do not graph this as a V. It has curviness to it. So it's supposed to look like an upside down U, not an upside down absolute value. So please be very careful. Next, we're going to go ahead and identify the information based on our graph. And we have domain. Domain, of course, is going to be all real numbers. Our range, well, based on this, it's pointing down. So that means that our lowest value is -infinity, going all the way up to our maximum value. And our maximum value, remember that is the y part of our vertex, and so that is going to be 4. So I'll have a parenthesis around -infinity and a bracket around 4. You can also say y is less than or equal to 4. That's another way to write it. Our end behavior, that is down, down. So that's going to be as x approaches positive infinity. So that's looking at it from the right. We have an arrow pointing down. We would say, well, this function is called g of x. So I'm going to write that g of x approaches -infinity. And as x approaches -infinity, which means we're just looking at the left side of the graph, we have an arrow pointing down. So I'm going to write that g of x also approaches -infinity. So there's my end behavior. We already know what our vertex is. That's going to be located at 1, 4. And now we're on axis of symmetry. Our axis of symmetry is always x equals. I will be specifically looking for the x equals because it is a line. An axis, a line of symmetry that is located at x equals h, and our h value is 1. Draw this in. I will be looking for that as well. Let's go ahead and draw in x equals 1. It should cut that parabola right in half. This has a maximum this time, and that maximum value is always the y part of our vertex, and that is 4. We have a maximum because it reaches this height and it falls right back down. In terms of comparison in words, that's the same language that we used before. So number 1, we will have a reflection across the x-axis. Number 2, we will have a vertical stretch. By a factor of 2. And number 3, we will have a translation. 1 unit to the right and 4 units up. All right, let's go ahead and move on to the next page. This next page has a bunch of solos, teams, and pairs where I just want you to have the opportunity to graph this on your own and come up with that table. So that compare means that I'm looking for a table. And you can come up with any ordered pairs that you want. I would recommend, though, using -2, 4, 0, 0, and 2, 4, just because of the fact that your A value is 1/2 and you will end up with the nicer numbers, but it doesn't really matter what values you end up using. The team in the pair is asking you to, without graphing, can you identify this information? And I think that you can, because this is basically piggybacking off of concepts that we've already learned, so I think that you can do this. If you want to wait until class time to complete this work, that's fine. If you want to complete it right now, that's fine too. The next thing I want to address with you guys is how to write an equation in vertex form from a table. So once again, vertex form is y equals a times x minus h squared plus k. And really cool fact about quadratic functions and their tables is that, you know how we have this square up here? That square kind of has meaning in tables, and it has quadratic functions have tables with constant second differences. If this was a cube, it would have a constant third difference. Linear functions have a common first difference because that degree is 1. So it's kind of a cool thing about quadratics. Whenever you're analyzing the table to come up with your equation, there's some hints that I need you to know. The first one is that the vertex is the point that is between the matching pairs in your y values. So you'll see symmetry just like we did in the parent function. Be careful, it might be hidden where that vertex is, and we can talk about that in specific problems. The next one we have is that the vertex will be the HK in the equation, which we already knew that, but this is just as a recap. And your A value in the equation, this is really cool. It is half of the second difference. So what you're going to do is say that A is equal to whatever the second difference is, whatever that value is, divided by 2. And there is your A value. So let's go ahead and look at this example really quick. So the first thing that I would recommend that you do is you identify what the first difference is. And what I mean by that is you want to ask yourself, how do you go from 11 to 7.5? Well, you would subtract 3.5. And how do you go from 7.5 to 5? Well, you would subtract 2.5. And 5 to 3.5, you would subtract 1.5. And 3.5 to 3, you would subtract 0.5. And then to go from 3 to 3.5, you would add 0.5. And from 3.5 to 5, you would add 1.5. So as you guys can clearly see, that first difference, there's no numbers in common. They all have a 0.5, sure, but they're not the same number. So now we analyze the second difference. How do you go from -3.5 to -2.5? Well, you add 1. And -2.5 to -1.5, you add 1, and you add 1, and you add 1, and you add 1. And what you see is a constant second difference. 1 is your second difference. So because 1 is your second difference, that helps you to identify your A value. Your A value, remember, is your second difference divided by 2. So that's going to be 1 divided by 2, and that will be your A value of the equation. So far in our equation, I know that this is going to be y equals 1/2 times x. And I need to look at and analyze my table. So let's see if I find some symmetry. 11, 7.5, 5, 3.53, 3.55. Boom, there it is. I see symmetry around 2, 3. And therefore, my vertex is located at 2, 3. And so because it is located at 2, 3, I know that I'm going to write x minus, because it's always the opposite of what I see, x minus 2 squared, and then a plus 3. There's my equation. My axis of symmetry, remember that is always x equals h, and my h in this case is 2, so x equals 2. My domain, that is going to be all real numbers. And my range, well, because my A value is positive, that tells me that my parabola is pointing up, which means that I will have a minimum value. And so this is going to tell me that because it's pointing up, my minimum value is going to be the y part of my vertex, which is 3, and then it'll go to infinity. Or you can write it as y is greater than or equal to 3. End behavior, because I know it is pointing up since my a value is positive, I'm going to say that as x approaches positive infinity, I called my function y, so I'm going to say y approaches positive infinity. And as x approaches negative infinity, y approaches approaches positive infinity. It's up, up. All right, please go ahead and try that next problem on your own, and we will talk about it the next time I see you. Otherwise, I hope you have a wonderful day.